This is Professor Robert Needing. You are back with Math 168, Section 3.1, Sampling Distributions. So in this thrilling section, we're going to look at the distribution of sample data, but however, we're going to start it off with a little bit of review to get you warmed up. You're interested in analyzing the relationship between political party and IQ. Okay, well, first of all, let's analyze what we have here. A political party is a categorical piece of information. An IQ is a quantitative piece of information. Whoa, too much there. An IQ is a quantitative. So you have one C and you have one Q. Write that down. You have one C, you have one C, and you have one Q. So if we take a look down the list here, number one. Well, number one is a bar chart. And the second I see a bar chart, I'm thinking about one categorical. Number two is a dot plot, and there's only a single dot plot happening here. And the minute I see a dot plot, it's one quantitative. Oops, one quantitative. And put my cap lock on. A side by side. Okay, now it's two of something. Two what? Well, it's two bar plots. Two bar plots means two categoricals. A side by side box plot. Okay, I'm getting close here. A side by side box plot. Box plot up here talks about quantitative. Does that mean two quantitative? No, because scatter plots are two quantitative. So we by default at number 4 are looking for one C and one Q. Knowing these by heart is really a great skill with inside the very beginning lessons here. Similar question, but now we have political party and gender. So if I look at political party and gender, political party is a C value, categorical. Gender is a categorical. Go back down that list we just made a second ago, and when we talked about two categoricals, we were doing side-by-side segmented bar plots. Number 3, we're interested in the gender of a voter in Lorraine County in a recent election. That is a single categorical value. When we talked single categorical values, it was number 1, pie charts, bar charts, proportions, frequency tables, and relative frequency tables. Again, knowing these is a key process to what we do. So our outline for this afternoon is statistical inferences, a statistic versus a parameter, a sampling distribution, the variability of a statistic, and its standard error, and the importance of size and the importance of a random sampling. So our n size and our random sampling. Standard error is a great pair of words to add to your, that was a terrible highlight job. Did you see that? I just highlighted everything I didn't want. Standard error is a great word to add to your vocab list at this point in time. So to put it into big picture analysis of what we're doing here, remember, we're looking at the population parameter, and that's the large group that we're going to sample from. Once we take a sample from a population parameter, we develop a sample statistic. Maybe X bar, maybe P hat. But when we get that value, we then make a statistical inference and we point it back at the population and say, I believe this to be true about the population because I had a random sample and I had no bias and my statistical analysis is sound. Again, we don't have time to get everybody in the parameter, but we can pull a nice statistic from a sample and we can make an inference about that parameter. And that's really the game here. Statistical inference is the process of drawing a conclusion about the entire population based on information in the sample. We want to make general, broad statements, but we want them to be mathematically sound. When we use this word parameter, remember, the parameter is a number that describes an aspect of the population. It's an average, it's a proportion, it's a correlation coefficient, it's something that has to do with a population. However, though, we never have that piece of data. That's an inference, and we draw those conclusions from a statistic. And a statistic is drawn from a sample. A statistic is also a number, but we calculate it on a sample because we can actually get our hands on a sample. We can repeat a process to a sample, And once we repeat a process to a sample, we can then make an implication about a parameter. Here's our generalized pieces of our parameters and our statistics. So if we're talking about a mean value is a mu in parameter, but its corresponding component is an x bar as a statistic. We would use an x bar to talk about a mu value. In a proportion, if we wanted to measure p, well, then we would have to use a statistical inference of p hat. P hat infers p. A standard deviation, this is when we're talking about the variance of something. And the variance of a population is referred to as sigma, whereas the standard deviation of a statistic is S, or a sample. The correlation coefficients are rho for a parameter population and R for a sample statistic. We have a couple here that we're supposed to try and come up with and give some good answers for. So for instance, I'll do a little highlighting here. Average. So first, average household incomes for all houses in the U.S. using data from the U.S. Census. First of all, average. Average is some kind of mean value. Now the question is, mean of all things or mean of some things? Well, it says all houses in the U.S. and we're using the U.S. Census. So therefore we have everything that we want, and therefore we have a population value. So the also asked us to use the proper notation. So I'm going to go over to my camera so that we can do a little proper notation work. Oops, there we go. So on the first one, because first of all, it's a mean average, my choices are mu or x bar. But because it's all things in here, it's going to be the parameter value. Parameter and mu because of all and because of average. I'm going to shorten that down a little bit too, so we can maybe make a little bit better there. I'm doing a little adjusting here, so give me a second. So now we're talking about a correlation. All right, so in a correlation value, we're either rho or we're R. And the question is it all or is it some? Well, the measurement's coming from 23 players on the World Cup roster. So that's telling us I don't have everybody. I only have a sampling of those people. So when I go back to switch over here, my correlation value will be R because I'm in the sample now, and I'm going to use a statistic because I'm in a sample. If I'm in a sample, it's a statistic. If I'm in a population, it's a parameter. A proportion of, so there's a key word, proportion of people who use electric toothbrushes using data from a sample. It tells you right there. So you know you want a proportion, you know you want a sample. A proportion is always p hat, and a sample is always a statistic. The proportion, here we go again. So we're going to take the proportion once again of all eligible citizens in Lorain County. So you might think you have a population. However, it's of those who voted in the U.S. election. Not everybody voted, and Lorain County isn't the entire U.S. So therefore, because it's from there, our eligibility here is just simply a sampling. So our Lorain County people stand for a p hat value from a statistic. Moving down, I have an average number, so that again is a mean, of houses in North Carolina using just 1,000 people. So once again, I have a sample, but this time my sample comes from a mean value. X bar of a statistic compared to average of a population parameter. The last one, a difference in proportions. So I'm going to have two proportions here subtracted from each other. And it's clearly from a sample because it says sample right there. Oof, messed that up, didn't I? It's trying to take the whole thing. Sample. There we go. So it is p hat 1, the 60-year-olds, minus p hat 2, the 25-year-olds, and it is a statistic again. Make this notation part of your everyday discussion in statistics class. A point estimate is a number for which we create a reference to a population parameter. It comes from a statistic. However, it points to a population parameter. It's kind of the point estimate. A point estimate will not match the population parameter exactly, but they are our best guess given the data that we have. Okay, that's why they're called sometimes best point estimates. If we want a point estimate for a population mu, what would we use? Well, the thing that corresponds with a population mu is a sample x-bar mean. This goes back to the very first slides. If we want a point estimate for a population parameter, a p-value, what corresponds with that? Well, it would be a sample proportion p-hat. Some important points here. First of all, sample statistics vary from sample to sample, and they will never match the parameter exactly. A key question that we look at and we talk about is the plausibility or the reasonableness, the possibility of the values of the population parameter. In other words, how much uncertainty, or we like to use the word variance here, surrounds the sample statistic. The key answer to this is it depends on how much the statistic varies from sample to sample. As the sampling varies, it will create a distribution. And as that distribution forms itself, it will form into a well-defined bell curve. And I'll show you that in a moment. A sampling distribution is the distribution of sample statistics computed for different samples of same size and same population. We'll be working with StatKey quite frequently in order to create those. A sampling distribution shows how the sample statistic varies from sample to sample. The center, if the sample is really randomly selected, and the sampling distribution will be centered around the population parameter, meaning that all of the dots will form themselves around the center of the true population mean or proportion. The shape of the statistic is large enough that the sampling distribution will be symmetric and bell-shaped. Let's go take a look at one. So let's say that I'm in StatKey, and let's just play with the distribution of a mean. Over here is the original population. This is 203 items that were thrown into this bucket. Now, what's going to happen when I generate one sample is that StatKey reached in, it grabbed out 10 things out of there, and it made an average of 41.92, and it plotted it right there. Now, remember, my average is 43, but just now I got a sample of 41, and I do it again. And StatKey did it again, threw everything back, and this time I got a mean of 46, and boom, it plotted it right here. Well, the average between those two right now is 44.29. I'm trying to see if I repeatedly do this over and over again, how close will I be to here? So when it says I repeatedly do this, and watch, now I'm building by 10 at a time. And what it's trying to formulate is trying to figure out, okay, where is the middle at? You can see the middle moving. And where is the variance? How far spread out from the middle is my data? Well, 10's getting a little rough. I'm going to jump up to 100. I'm going to do 100, another 100. And what we're trying to see is a well-defined distribution. Well, I'm not really not seeing anything other than a bunch of flat dots so far. Let's jump to 1,000 and watch what happens. And you'll see it start building, and you see what you think is about to come into the picture is a well-defined symmetrical bell curve. Now we got a little spike going on right here, but for the most part, we're doing pretty darn well with a nice curve going on here. Remember what the middle was, 43.024, and we're at 43.124. We're pretty darn close. Also, please note right here, if you look right there and where my mouse is hovering, this is the standard error. The standard error is the standard deviation of the sampling distribution. The standard deviation out here is part of the population, the original data. The standard error is always part of the distribution of all the repeated values. Okay, standard error only happens in the sampling distribution. Sampling cautions. If you take a random sample, the sampling distribution will be centered around the true population parameter. We just saw that take place. If sampling bias exists, you do not take random samples. Your sampling distribution could be flawed. You could have bad information. We've learned about center and shape, but what we really care about is variability. Remember, the key question is if we need to know how much the statistic varies from sample to sample. And that's what I just showed you when we were here. The standard error of 9 says that from the middle here, if I went up approximately 9, about 53-ish, 52-ish, and I went up again to about 61, I would contain about 2 standard errors. And if I click my two-tail right here, you're going to notice up here, that stops my 2 standard errors, and this stops my 2 standard errors. Remember, all data is 2 standard errors up and 2 standard errors down for 95% of the data. Pretty cool, I know. The variability of the sample statistic is so important it gets its own name, and I just used it over and over again as the standard error of the statistic. The SE is the standard deviation of the sample statistic. Know that box in and out. The standard error measures how much the statistic varies from sample to sample, and the standard error is calculated as the standard deviation of the sampling distribution. Again, it's the standard deviation of all these dots when we distribute them. Okay, the standard deviation truly takes place here. The standard error here is the distribution of these, and it can be read right from this data. We're going to estimate the center and a standard error from a couple of pictures. These are very easy, but for some reason, students really don't like these. They struggle with them, but you shouldn't have a problem at all. So I'm going to make this a 4. So first of all, to find the middle, all we got to do is look for the number in the center. Well, the number in the center has to be 30. Why does it have to be 30? Because 37 is too far to the right and 23 is too small down. So my first value that I'm going to write down is my proportional center, which is 0.30. Now, how much does it go up and how much does it go down on each side? All right, well, remember, there's got to be 2 standard errors on each side. If this is 1 standard error and this is 2 standard errors, and you want a couple of dots on the outside, then your SE is 0.07. Because remember, 0.30 plus 0.07 makes 0.37. Remember, you'll also have 2 of them down here, minus 0.07, minus 2 times 0.07. There'll always be a few dots on the outside. My standard error for this particular shape is 0.07. On my second one, I'm going to estimate the center and the standard error from the sampling distribution. Again, it's all about finding the middle. I think we can all agree that 300 is a nice place to start the middle. So if I start the middle here at 300, whoa, bad drawing, right? And I let it count down 2 notches. And by notches, I mean 2 sets of numbers. And I let it count up by 2 sets of numbers. I will contain, I'm going to make these oversized here on the ends. I will contain approximately 95% of the data inside this center curve. Everything under here contains approximately 95%. So what does that leave me with data? It leaves me with a middle of 300, and that leaves me with a standard error, approximately 5. The measurement of error would be 10, because the measurement of error is from here, which includes 2 standard errors, but the standard error is 5 on each side. It would never be 15, because then I would lose too much data. I need to leave about 5% of the data on the outsides of the curves. Now in this one's a little bit different, and it asks us something different. It says, indicate whether the proportion is I, reasonably likely, II, unusual, but might actually happen, extremely unlikely, III. Okay, well, I'm going to do exactly the same thing we just did a second ago. If the center is at 30, 0.30, and 2 standard deviations takes me up to 44, and 2 standard deviations takes me down to 16. That means that underneath of here is where most data takes place. So if something falls under here, it's likely. If something falls close to the lines out here, it's unusual. And if something gets really far away, it's pretty unlikely, but it still can happen. So 0.12 is right about here. That's where that data point is. Well, that's kind of close to this line. So I would gauge this particular item, 0.12, as being unusual. But, however, at the same time, it might occasionally occur. Now I'm going to go do 0.35. 0.35 is dead underneath of the curve. That thing is likely to happen. So this is an I. It's a reasonably likely item. And I know I'm not answering them in I and I and all that, but I'm writing words for you. The last one, 0.62, that bad boy's out here. Now, we can't say that it won't happen because there might be a dot out there that we do not see, but this thing is the extreme unlikely. It's probably not going to happen, but we can't, oops, whoa, just lost that. We can't say that it won't take place. So it's extremely unlikely. Sample size matters. As we change the sample size, we tend to decrease the sample statistic, and it tends to be closer to the true population. It goes on to say, for a larger sample, you'll get less variability. Remember, the variability is the spread of the estimate. So in this question, we have three different pictures. A is spread out extremely. B is spread out not so much. C is very compact. We would pick the ones over to the side which correspond to that. For instance, if you only have 20, 100, and 500 things, the least smallest item is going to be the most spread out. This is going to be sample A. And then I'll do the largest. The one which has the largest data value is going to be the most compact. This is going to be C. And from here, you're going to have letter B. I'm going to leave these for you because these are worthy of you doing inside of Wiley. This will get you started nicely, and then these questions will come from me giving you these answers. Wiley question number 3, I'll help you out with. It says, for sampling distribution of Major League Baseball players' salaries, each dot in the population distribution. Okay, now remember the population distribution value comes from all those players. And the correct response would be that this is the salary of a randomly selected baseball player. Okay, because we're talking about, it says each dot. So each dot stands for a salary of a baseball player. When we go to the same exact question, but we change it to each dot in the sampling distribution. Now, remember the sampling distribution, this is the average mean salary of a random selection of 50. They're getting you to show the difference between the population distribution, the sampling distribution, and right now, the center of the sampling distribution is usually centered around the population parameter. So now they want us to determine what the heck a population parameter is. Let me highlight that too. Okay, remember the population parameter talks about everybody. So therefore, it's the mean salary of all, there's the key word, all major league players. In summary, statistical inference is drawing conclusions about a population based on a sample. We take a sample and we base our values on that sample statistic. We use sample statistics to estimate this population parameter. Remember, the population parameter is the statistic that we do not know, but it stands for the population. We assess uncertainty of a statistic. We need to know how it varies. How much does it leeway from the middle? This we know is the standard error or the standard deviation of the distribution. To create a sampling distribution, take many, many, many samples. You saw me do that with StatKey, and compute a statistic for each. The standard error is the standard deviation of a statistic. When you come back in section 3.2, we are going to continue on, and we're going to be talking about confidence interval levels. I'll see you then. It's been enjoyable, and I can't wait for it to happen again.